In the demonstration you saw with the balloons, once I charged up the balloon with my head and my daughter's head, do the balloons need to be in contact with each other to exert those electrostatic forces on each other? Well, of course not, right? And when have we seen that before? Hopefully remember, of course, with the gravitational force. And what do we need to establish to describe this force acting at a distance? That was the idea of a field, right? So let's do a side-by-side comparison in our notes between a gravitational field and a new form of a field called the electric field. Now, we've taken great pains to show that the gravitational force and electrostatic force are certainly not the same thing, but, as I mentioned, there are enough similarities that we will keep going back to what we know about gravity to help inform us about electrical effects. Let's start with the original definition for gravitational field. We always said that a field will be defined as force per something, so hopefully you remember that our original definition was that G is F sub G over N. It's always going to be force divided by whatever it is that an object has that allows it to experience the force, in this case, mass. And then from this we got the original units for gravitational field, which are newtons per kilogram, literally force per mass. Well, wouldn't you know it, we're going to follow the same routine for establishing our equation for electric field. Our symbol for electric field is going to be capital E. What force is associated with the electric field? Well, of course, it's going to be the electrostatic force. And then what property is it that objects have that allow them to interact in an electrostatic way? Well, as we've already talked about, it's going to be charge. Now let's put that charge in absolute value. This way, this equation will get us the magnitude of the electric field. We don't have to worry about any sort of direction. We'll talk about the direction in just a little bit. What units would electric field be measured in? Well, I think you can clearly see there's going to be force on the top and charge on the bottom. That's going to be newtons per coulomb, very similar to newtons per kilogram. Electrostatic force is a vector, charge is a scalar. That means electric field is going to be a vector as well. And so we can identify this as a vector quantity. And we can box it in as our new equation. Let's define our terms. We have to be very, very careful here. So capital E stands for the electric field strength created by some other charge. Now that may seem a little bit strange with the wording there, but trust me, this is going to become a little bit clearer as we go through it. Now we did say we're taking the absolute value of the charge that's in the equation, so that's not going to contribute to our understanding of the direction. Here's how we establish the direction for electric field. The direction is whichever way a positive test charge feels a force. And I haven't defined what a test charge is yet, but I will soon. And in fact, the test charge is the charge that's in the equation. So if you suspect there's an electric field in some location in space, you put a charged object there and see what happens. This is the test charge. You're testing for the presence and the strength and the direction of the electric field. Now ideally this test charge should be a small amount because the test charge itself will have its own field and you don't want it to disturb the field you're trying to measure. Now this is what's so important. This test charge is not the charge creating the field. It will have its own field, but that's not related to this field it's trying to measure. And that's why we said this field is created by some other charge, not the charge in the equation. Confused yet? Well, don't worry. We'll try to make it as clear as possible. Now, just to be very clear here, the electrostatic force, well, that's the force experienced by the test charge. They go together. So this is the charge you put in the field. This is the force experienced by that charge, and this is the field you're trying to measure. If that's a little bit confusing, well, let's go back to gravitational effects, because even though gravitational effects and electrostatic effects are not the same thing, we can again use what we know about gravity to help inform information about electrostatic effects. So, in this equation, let's say this is you. You're that mass, and this is the force of gravity that you experience. Well, what's that called? That's called weight, right? Remember, force of gravity and weight are the same thing. So, here's your mass, and here's your weight, and then here's G. You experience a gravitational force because of some sort of gravitational field. Now, is this your gravitational field? No. Whose field is that? Well, it's the Earth's, right? You experience a force of gravity because of Earth's field. This is you, and this is the field created by some other mass. Well, hold on. We said that this field is created by some other charge, right? Not the charge in the equation. The charge in the equation here is the test charge. Well, in that sense, you are the test mass, right? So we can measure Earth's gravitational field by measuring your mass and the force of gravity acting on you. Okay, so again, here's you with your mass. Here's the force of gravity you experience because of someone else's field. So here's this test charge. Here's the electrostatic force it feels because of someone else's field. Yeah? Okay, let's go back to gravity. So here's you again. Now, do you create your own gravitational field? Hopefully you realize, yes, we've talked about this, right? Every single mass in the universe creates its own gravitational field. Just your gravitational field is much smaller compared to Earth, so you don't really notice it. But yes, you create your own gravitational field. Okay, so you create your own gravitational field. Is that this field in the equation? No, of course not, right? This is Earth's field. So you create your own gravitational field, but the field in this equation is someone else's field. So going over here, here's a charged object. Does it create its own electric field? Yes, it does. Is that this field in the equation? No, it's not, right? They are completely unrelated. This is the test charge that is experiencing someone else's field. Just like this is you, your mass, experiencing someone else's field. I know this gets a little bit confusing, but it's going to become clearer and clearer as we go through more examples of this.